All right. Good morning, Alan Murray from UC Santa Barbara, as it says here. Happy to be here. Packed audience. I've never seen a bigger crowd.
Hopefully the cameras.
Is it? Is it?
The camera's on.
See? All right, so today I'm going to talk about something that's particularly important in Southern California more generally, but definitely in Santa Barbara, where I'm from, looking at evacuation potential and looking at this from a neighborhood-oriented perspective. I'm the director of something called the Wildfire Resilience Initiative at UCSB. The initiative is actually supported by a private foundation in terms of donation. And really the idea behind the initiative is a recognition in Santa Barbara for the 9 years that I've been there. We've been evacuated over 5 times because of wildfires. Most of the region is really at risk in some way. Wildfire in this place. Were you ever evacuated, Crystal?
Yeah, a couple times.
You?
Go a few hours away.
So it's a big deal, but the idea behind what we're doing in this initiative is bringing together people across the UCSB campus with expertise in some aspects that are important looking at wildfire risk and vulnerability, to bring them together to address aspects of understanding the vulnerability, but also to develop mitigation approaches for dealing with wildfire vulnerability. So in terms of what we have right now, there's an expert in remote sensing and the monitoring of vegetation conditions. So remote sensing is Doug Roberts, some weather and climate people, Layla Caval, Charles Jones, expert in fire behavior, Max Moritz, who's a graduate of our program, but also the UCE outreach, wildland fire specialist. And so all of us, and then on the social side, Stuart Sweeney, and then myself on the side, so dealing with the human condition. So bringing all of us together, putting us in the pot and stirring it and seeing sort of the kind of good things we can do in conjunction with Fire Safe Council, Forest Service. So Santa Barbara is sort of interesting because there's this mix of different agencies and municipalities, and then doing things to address these components. So what I'm going to talk about today, this evacuation component, is a part of this sort of bigger picture. So evacuation as a process is about moving people from a dangerous location to a safer location. And really the idea is always the fewest people necessary. So move them out of harm's way. And then in Santa Barbara, believe it or not, earthquake, tsunami, there can be impacts in our region. Flooding, storm surge, coastal erosion, cliffs are eroding all the time, landslide, debris flow. We've had hazardous spills along major roadways, but fire and wildfire in particular is probably the biggest one that in terms of evacuation we face on a regular basis. And then in terms of evacuation, it really does imply you have a place that isn't safe and that there are places that are safe, and it really is context dependent. And so in terms of why you would evacuate and how you would do it, there's why, where, when, who, all of this is really context dependent, and there's a lot of factors that go into who we evacuate, the timing of doing this, and what people are going to do and what people won't do. But typically, in terms of evacuation, we really hear these big regional scale oriented evacuation efforts. Hurricane, evacuate areas of Florida. And so these are big, massive regions. So that's the typical focus. But really, evacuation happens on a daily basis that is very concentrated, a neighborhood or community oriented. And there's lots of examples, but maybe I'll just focus on most recently. In the Los Angeles area, there was a number of fires, but a lot of press looking at Pacific Palisades and the Eaton areas were examples of very localized the need to evacuate people out of these areas where fire was imminent. And so that's in this talk, really what I'm talking about is this local, community-oriented, a small area, we need to evacuate them. And in particular, so as it says here, typically it's a regional focus and an interesting, so here's a person who's a big name in evacuation modeling, but this quote is pretty telling. Because it's viewing that the small scale or neighborhood oriented evacuation is really something that can be improvised. Like when it happens, we'll deal with it. We don't need to understand it in advance or have really some idea of what we need to do in advance or engage in some mitigation. So in a way, the neighborhood scale is sort of dismissed by most people focused on evacuation modeling. But yet, it's really the most common thing, and it occurs very regularly, but there's almost no analytics to support either identifying or how to deal with or mitigate or address issues associated with this neighborhood level evacuation. So what I mean by that, so this is an area in Goleta. There's about 149 homes here, and all of these homes exit through this one road. And so this is an area that's particularly vulnerable. If there's an accident or something else, people will not get out. And so 149 homes, it's usually like 2.5 people per home. If you want to estimate the total population, it's a few people. And so this is really what we're talking about, the ability to look at the transportation structure and identify where there's lots of people with minimal exit or means of egress to get out. And then in doing that, when we understand that, well, this is an area, there's quite a few people, and then we understand where these sort of limiting areas to exit are, we can do something to ensure the flow of traffic in that particular really critical location. That's really the idea of all of it. And so depending on what literature you talk about or you look at, they might call this a bottleneck point, pinch point. In graph theory, we talk about it as a cut or a cut set. Tom Kova, who's a graduate of our program, and Rick Church, who's a maritime faculty, they talked about these areas as critical clusters. That is, a lot of people, but few exits. This is actually Pacific Palisades, so one of the areas burned in Los Angeles. And you can see in this area, there's 1,300 people that live in this portion, technically one exit. In practice, there's actually a fire road here, but the fire started in this area and soon just even the fire road, which fire road is supposed to save the area, it was inoperable, right? And so 1,300 people for one exit, and I have a video at the end, but you may have seen on the news, a bulldozer moving these cars that people abandoned. This happened right in here, Sunset Avenue and Pacific Palisades Road. And so this was a congestion point, a bottleneck. People couldn't get out. And then they were told by emergency personnel to abandon the car and run, which you never really want to do. But that's what happens. You're usually safer in the car than a human against a flame. You're never going to. So that's really the idea. And so coming here, I thought I'd give you what really are these underlying research questions. So one is, how can we identify these vulnerable neighborhoods that are potentially difficult to evacuate? Second, what strategies can we employ or develop to help ensure sort of the safe evacuation of these areas? So a big one, for example, might be the typical consulting suggestion would be, oh, let's put a roundabout here. Because that helps move traffic in certain sort of ways. It would be unrealistic here, but typically when we talk about evacuation and private consulting reports, it's always, oh, a roundabout. Not necessarily a good idea, but it could be that I man it with emergency personnel to keep traffic flowing and come up with other sorts of measures. Maybe I have appointed community people that are going to be there to help ensure, like if there's a stalled car, I move it out of the way. But under evacuation conditions, all sorts of weird things happen. People hook up a trailer that hasn't been moved in 10 years and it gets a flat or something doesn't work. And then this is the bottleneck, right? And what you're trying to avoid. So you need these mechanisms and measures to help ensure this flow of people. So as if this isn't, I think all of these are sort of important enough, and getting people out is recognized as important enough, but there are California government codes, so legislation-based measures that say really we need to understand these means of egress, and then typically in terms of development, do things to plan additional ways of exiting and sort of other things. So there are research questions, but there's actually California law that requires this sort of evaluation, but yet no analytics to support this. And so today I'm really going to be focused more on the analytics side, but I mean, this is all driven by practical need, and that we're doing these for communities for important reasons. So again, we have our transportation network, and in terms of like the bare bones analytics to do this, it's a network, right? A network consists of nodes and arcs, and that these arcs are the roadways, and the nodes might be the digitized endpoint of the road segment, or they may be actual intersections in the road. Like, so for example, nothing's here other than I digitized the segment and it ended here, and then here's another point. So however, it's represented as nodes and arcs, and in terms of what we're trying to do to identify these critical areas is look at it from so we want to look at the network, look at the characteristics of the population distribution, and identify areas where there's lots of people but few exits. So we're coming at this from like a decision-making perspective, looking at my network, where is this interesting critical cluster and where are these limiting exit points? So it means I structure this as an optimization kind of model where I'm trying to decide which nodes are a part of this interesting cluster or neighborhood. And then secondly, what are the road segments that define this limited egress, the bottleneck points, right? And so you can see here, should this node be included? Should this node be included? That's sort of what we're deciding. And part of whether we would include it or not depends on how many people reside in or around that area. And then secondly, I'm looking at links and saying, oh, is this a link defining this cluster I'm defining in the outside world or not? Because I need to know who's in the cluster and then how many of these exiting or egress links there are. So this is sort of the context. Analytically, so I mentioned Tom Cove and Rick Church before in 97, they talked about this critical cluster problem. And they said, really, it's this objective of the maximum number of people divided by the minimum number of exit points. So really, this is what is characteristic of a critical cluster. So if I think about it and look across my network, I'm really interested in what's that area with the most people, greatest limitation of getting them out. And whether that's something I need to consider sort of depends on what's the potential hazard, right? So if it's an area, it's in the middle of downtown Santa Barbara, it's probably not a big deal. If it's an area that's in the foothills, right next to the wildland urban interface, where there's vegetation, that's dried out and other sorts of things, that's probably a big deal in terms of wildfire. Is it an area, as we're going to see, near the coast where storm surge, tsunami threat, flooding, whatever, then maybe that's another sort of an issue. So it's all context dependent about whether it's low. So the idea then is to identify this area that has this highest ratio of people per exit. And so Cove and Church talk about this as that ratio really represents a function of the clearing time of that area. Or you could think about it from a transportation perspective as sort of bulk lane demand. And so to do this, you need some constraints to track what defines this bottleneck segment, right? This segment that connects the cluster to not in the cluster. And then in terms of what they did, I won't go through it, but it's got to be contiguous. They don't talk about the constraints for doing this, but as a model, we would need this. So in terms of this as a model, well, one, it's a nonlinear optimization problem. From an integer programming perspective, this is like a nightmare. Super difficult to solve, unlikely that we would be able to do anything just because of the objective function. Secondly, they just say, well, we need contiguity constraints, and they don't really talk about them because that's hard too. It turns out we can do it, but in 97, it was like unthinkable in a way. And so what they talked about a few years later was a way to take this difficult functional analytical model and try and linearize this. And so what they said is, well, what if we set some parameter on what this ratio should be? And then we just adjust the parameter. And in a way, we do something to the model where we can control it externally or a priori and then solve it. And it turns out that this was a good first step of coming up with some linearization. And so what they did is move this ratio as a constraint and then just say, well, I can change. Yeah.
I think I missed from the prior slide. What is C? Remember X and Z?
C, oh, this is the capacity of a line segment. So I could have a lane that's got 2 lanes or 3 lanes or 1 lane. So that's just indicating how many lanes are a part of that segment. Good question. You didn't know it because I didn't tell you. Okay. But and so anyway, the point then is that they took this nonlinear objective and then move it as a constraint, and then they could, play with this parameter to adjust basically this ratio of how many lanes. So I could look at identifying this critical cluster when there's only 1 exit lane or 2 exit lanes, and I can evaluate a whole series to then assess that. But still, so this looks pretty good from a linear integer programming perspective, except there is still this issue. And so, 3 years later, they did talk about this and say, well, we can come up with a set of constraints that will ensure contiguity in this model and then solve it. So super difficult problem that originally they solved heuristically and then ultimately came up with a kind of linearization. It's still sort of an approximation. But technically, this is a huge number of constraints. So it's in a way problematic in practice. So in terms of considerations here, I gave this talk or part of this talk at a conference in February, and Rick Church was there. So I was really polite in how I said it or anything, like, oh, great approach, elegant approach for linearizing this difficult thing. If he wasn't there, I probably would have said it like, yeah, it's not very good, but it's great. He was my advisor. Definitely. I had to be super polite. So one of the things that they did in their approach is they said, in our linearization, what if we solve it initially by ignoring contiguity? And then we'll cross our fingers and hope maybe it is contiguous. And then what they did is they showed that you could do that. It's usually never going to be contiguous, but then they could add iteratively constraints to make it be contiguous. And so rather than millions of constraints to impose contiguity, they could just selectively add these things in an iterative fashion. And it worked and is pretty good. And so you can see here we talk about solving optimization models, anytime we see this sort of, it's a function of, so omega is the number of nodes. And so the number of nodes squared, anytime we see a factor of these squared or higher, that's really a problem. And so it did work, but I mean, worst case, it's not particularly good. And the second, and I didn't really want to get into it because I'm going to show how to really do it better, is that how they structured the model really over parameterized it. So basically, to get a cluster, you're almost locking it in. You need to know the number of members of this cluster to begin with, and we never know that. So a lot of the way that they structured the problem isn't really helpful in practice. So I'm gonna give you the gist because we don't probably have enough time for me to get into a lot of the nitty-gritty details. But what we have as an objective is I want to identify this area of the most people. So that's really what we're trying to do, this biggest area. And then in the approach that I'm taking, I'm really setting in how many exits. So find the most people with one exit, and then I could change lambda and say, find the most people with 2 exits. And so that part, no problem. And then all these constraints are just tracking what's the exit of this cluster. And then finally, one of the elegant things about the Cova and Church approach is that they said, if you thought about what's this critical cluster, the most people with the fewest exits, and I looked at a whole region, it would just find one, V1. But in fact, there could be many of these clusters. And so what they said is, well, for every node in the network, I'm going to generate what's that critical cluster that involves that node. And if I do it for every node, then I can, after the fact, look at all those and say, which ones do I care about? And so that's what this really represents. And then ultimately, how I've set this up is as a flow problem, where the cluster itself generates flow that goes to some sink. If you're into network theory, there's really a network flow kind of aspect that's all about sources and sinks. And so how we set this up is that I have one source, which is the critical cluster, and then those people go to some sink, and then everything else goes to another sink. So really, it's just structuring to say, I care about the critical cluster and then everything else. But also contiguity constraints. And then we talk about a way to do this. And in the geographic literature, there's been a lot of work initially by Church. He was a part of it, doing something else, but then a person named Sharabi developed some constraints to do this. Not exactly this, but what I'll point out is, in contrast to what Church and Cova talked about, this is just a linear number of constraints. And so I'll jump to the bottom line is that in our case, there will be thousands of these constraints. And in the case of Church and Cova, there would be millions, like 6 to 8 million. Really a huge difference, enough that you couldn't even solve it in how they structure it. So I can come back to this, but the tricky part of the formulation is the one element where I track the exiting constraints. And all I do here is show that under every situation where I looked at 2 nodes, I and J, what I'm trying to track is the case where one's a part of the cluster and one's not. And in that case, that defines one of these lanes of egress. And so basically what I show is through these constraints, all the conditions are satisfied. So you can trust me in that, oh, it works and it's right. The second thing is imposing contiguity. So the idea is that assume that all of these nodes had people there and they were part of this critical cluster. And the idea of the constraint set is that the demand at each of these nodes represents flow in the network. And so if it's selected, it has to send that flow to some sink. And in this case, this node's defined in the model as the sink. And so all of this flow has to end up at the sink, which means it has to be a connected subgraph in the network. And so the constraints really impose this condition, but that's how it's working. It's basically this network flow idea. So I'll get to some of the practical considerations and output from doing this. So Santa Barbara, Luke used to live up in here. Here. The campus is out here. So that's the lay of the land. There's about 200,000 people in this Front Range region. Santa Ynez Mountains are here, and the mountains are full of chaparral, and chaparral likes to burn. And so we don't let it burn, and then we have people near things that like to burn, and that's part of the problem in terms of wildfire. But in terms of the area, as I said before, there's tons of these hazard conditions that could arise that would entail associated evacuation. You can see some of the characteristics of the region. And in terms of some of the details, if you care, so evacuation in these neighborhoods, it's a part of a bigger process. Like I have a transportation system, I have people, right, that would have to be evacuated through the transportation system. There's the GIS component of all of this, like I have to do some interpolation of what I know about people in some polygon units and then interpret them in the network and then in nodes in the network in particular. So there's all sorts of GIS oriented things. And then I talked about the modeling part, right? Then there's this model to identify what are these critical clusters. But then once I have them, I would be doing something like a basic simulation of the movement of people to understand like these flow dynamics and whatever. So all I'm trying to highlight here is that through this process, we would understand what's happening. We would look at it in the context of particular hazards, and then we would develop, perhaps in some areas, some mitigation strategies for dealing with more efficiently and more safely moving people and property under particular conditions. In terms of implementation, so this is in Python, relies on libraries in PySal, GeoPandas. We use a package, integer programming package called Garobi. It's sort of, I guess Cadillacs aren't the nicest car, but it's, the Mercedes, or what's the most luxurious? It's the Lamborghini of cars or whatever, maybe, of solvers. It's really the best of the best. In terms of the structure in the Santa Barbara area, there's over in this particular region, there's close to 7,000 road segments in terms of, and that's more or less a function of how it's digitized, but some of the structure of intersections. A little 6,200 nodes in that network we would consider populated. Like there's a lot of nodes in my network that are 101, which is a highway, no residents there. So some of those aren't considered as populated areas. The resulting model, if you care, it's 100,000 constraints, 78,000 decision variables. Typically, when we solve these things, it's a matrix of rows, which are the constraints, and the columns, which are decision variables. And then the process works basically with that kind of matrix. In terms of neighborhoods and a parameterization, we considered neighborhoods of like 4,000 people, but we also solved it in a case where we considered bigger size neighborhoods as well, up to 25,000. Solution to solve this. So the data processing, it's 2 minutes to do the data processing. This is just on a laptop. Nothing special. The model, to set up the model, right, to do all the things to specify model and whatever, that's about, half a minute, and then to solve it's seconds. And so the significance here is that this structure, this network structure in the model is really amenable to a very fast solution. It's really quite remarkable, actually. How I did it, not how church. I'll show you. Carpinteria, Luke's been there, maybe you've been there, Crystal's been there, maybe. So here's an area in Carpinteria, just as an example. These limits, and I said, oh, let's find a 2 exit. And so here's one exit, and then here's another exit of this whole neighborhood. And in terms of people, there's 2,500 people, and so 1,200 people per exit lane actually is quite big. In terms of original, there's no standards on, well, what's a big deal? Like, what's the number of people per exit lane? Church and Cova said it was 500 or more. So, I mean, by that standard, this is pretty significant. In this area, there's flooding, big deal, earthquake, and you can read the others. But in terms of the model, like, we can set the number of exits, solve the model. How long did it take? 7 seconds. What was it? 500 people per exit lane. For 2 exits, it's 1,200. 3, it's 700. So you can see it's going down. So the most significant one is this 2 exits. So in terms of the model, by specifying sort of this ratio and parameterizing it, you can control it, and you could, and indeed what Church and Cova did to make this nonlinear model linear is quite ingenious. Really a good way to deal with what is a really big computational challenge. So that's one. I'll show you an even more significant one. So this is the UCSB campus, and then next to it is something called Isla Vista, where most students live that aren't in dorms. I'm sure Crystal may have lived in Isla Vista. Did you ever? Never?
Oh, not.
You
not
avoided
maybe.
it. You missed out. Okay. I lived there as a student. So it turns out this population of this area, including, there is some student residential population. It's about almost a little less than 25,000 people, and it's limited by 3 exit lanes. Right here on Stork Road, there's Carneros, and then 217, this is a highway to get onto campus. So 3 exit points, and that's 2,400 divided by 3 gives us over 8,000 people per exit lane. And there are a lot of significant potential situations where one might need to evacuate this area. And in doing so, the campus is screwed, right? Because it's not only this population, but this is really residential population. So it's not counting the 1,300 faculty, 10,000 staff, and people that aren't residents of this area that are coming in to go to school and whatever. So depending on time of day, this could even be more people in terms of the exit. But again, I can look at all the potential exits and I can see this is the most significant one and why I would care about it. So what we have then is this analytical method to help identify these particular critical clusters of the region. And so we can do this for the whole region. And that's what you see summarized here is you see this scheme, this darkest red is over 3,000 per exit lane. And so you see the campus, and then this is the Carpinteria area we were looking at. But there's many, many others. So a significant one in terms of wildfire is this sort of El Encanto area, which is over 1,300 people per exit. Big deal. And then an interesting, in Santa Barbara, Mission Canyon, which is this area right here, is always thought of as really the most dangerous area. It's all surrounded by chaparral, super windy roads, narrow roads, very difficult to potentially evacuate. But it's less than 500 people per exit lane, technically. But, so this is one element, right? Exit is part of it, but it doesn't account for the characteristics of the road, how narrow it is, whether there's street parking, those sort of elements that may be contributors to difficulty. But what we have here, and this is, I'll show it in a minute, online, that anyone can look at this and evaluate what this is for any area of the region. But you really see quite heterogeneity in terms of what this looks like in the region, and then whether it matters sort of depends on the context. Not all areas are going to be a big deal in terms of wildfire, certainly not in the downtown area, and other sorts of things. But to do this, to support this, meant that from an optimization problem perspective, we had to solve this for each node in the network for two different kind of parameters in terms of cluster size. So that means over 62,000 problems were solved. And so kind of a lot, but really just a couple of days of process in terms of this overall. And yes, I can go to the site, but so this is all online in terms of our initiative. You can see this. And the map is sort of a backup in case I have a problem. So it's all interactive, and then there's a lot of other layers that I'm going to turn off, including live fuel moisture and whatever. So like I said, all of it depends on context. And so we have all these other layers of looking at hydrant spacing, looking at structure to hydrant access, looking at live monitored real-time live fuel moisture, and whether the vegetation sort of in a susceptible state. But there's climate and weather because of certain conditions in Santa Barbara, something called sundowner winds. Certain areas are more prone to really these high 90-mile-an-hour winds like we saw in Los Angeles that really drove the fire and resulted in this major conflagration that we saw. And so the point here is just that you can interactively zoom in on these areas, look at what are the number of people per exit lane, I think is what this is. So you can see, oh, it's 1,400 people per exit lane, and then evaluate them relative to some other elements. And I think and then you could also see it in 3D, like with this live fuel moisture. So like these areas, this darker color means that that vegetation is more susceptible. I think in this case, that's sort of an error because the area burned. And so it leaves a funny spectral signature in the crop sensing. But this is the point, is that it's this interactive environment that we can look at these analytical results. So most of all of these layers are things that we've derived in advance, and they're not in real time. And one of the reasons I'm here is to think about ways that we might be able to do this, like GeoDa, in real time, and support that in that way. So this will be, I think, automatically playing. You can see the bulldozering it. Super important. And in contrast to really what's perceived or thought of, it's all not neighborhood. Doing so, that's where we have this, because we're not in advance Sure. Really hard, because that is not what you want. Second thing, as a discussion point, study that's worked with file data, open source, heat map data, or data from providers, and for line segments. Don't look at it. It looks everything looks fine, but really coinciding problems with intersection, processing things like enforcement, up these things, and all of a sudden you have underpasses, the road thinks that incorrect intersection. And that's really problematic. And network structure, so what's limiting people? So the network, that's been a month. Thinking after the analytics part was a small function, much less. That's kind of sad. We have this perception that we have all this great data, it's available, use it, and coaching, if you got rid of it, rely on precise network structure, if it's not there, we have huge problems. We really have no mechanism of establishing what is something we should care about in terms of number of people per lane or whatever. And so there are no hard and fast, reliable rules of what should I care about at which point. Is it 500? Probably not. Like in transportation, you're usually thinking more on the congestion side of 4,000 or more. But that's not true either. So for these communities, hundreds, but thousands for sure are a big deal. I didn't go into a lot of details, but in 1997, Church and Kova, they developed some heuristic technique to do this. And that's okay. Although I could, if I'm not out of time, I can show you how they sort of miss some really important clusters or these neighborhoods and how they did it. And partly is what the heuristic sort of did to generate these things. But solving it optimally is always like the standard. That's what we're trying to do, because then if we develop some approximation or heuristic technique, then we can compare how well it's doing. We will always care about these approximate techniques because usually they can be super fast. So whereas for this whole region, it took 2 days of computation to find this, it could be that with some heuristic technique, I could find these in a minute or 5 minutes or something like that. Maybe. It's still not clear whether it's true. But then if I did that, I could at least compare if I've solved it exactly with and understand how well I think it's doing. And so the development of exact techniques is always going to be important because that's really the standard of what we're trying to do. And then any other approximate techniques, we would compare to that. Visualization, how to visualize this, it turns out to be a big deal because in what I showed you from a map perspective was a summary. And so in doing this, I'm doing it for every node and saying, you're a part of this cluster, what's the biggest one and the limits based upon the constraints I'm looking at. But then to assemble this, I have to go through and say, okay, this area was the most significant. So now I can't include any of these nodes and any of the other ones that I found. And so I'm piecing it back together, but one might argue that it's sort of a heuristic process. And so the ability, to visualize this and understand this in some ways, probably something that needs more attention and work. Just to put that out there. So neighborhood evacuation, very distinct. I hope I've sort of made that point. We don't really have in place good analytics to support doing this kind of work, and it's essential. And it's essential because it's actually codified in California law. So there are many reasons other than, as a person that lives in an area, I care about this and we want to look at these things and understand what we're doing. And to date, there really hasn't been a way, there hasn't even been a recognition that this is sort of a problem and an issue that we need to address. The capabilities, through like the modeling work that I talked about have been, hugely extended. There has been, some discussion, and I know that Tom Kova has applied heuristic and other processes to do this, but it's really what we know is that it's kind of an approximation of what is truly these critical clusters. So it's really advancing sort of our capabilities in a huge way. In terms of how they did it, I think I added, I'm not sure if this was in the talk when Church was there. I may have left this out to ease the pain for him. But to solve the problem that we did would be over 6 million decision variables, 8 million constraints. Just to process the model took over 40 minutes. And then it said, yeah, can't solve it. So not even possible. It wouldn't even be possible by their techniques in a formal sense. And then, there's other sorts of things that still need to be done. And with that, where are we time-wise? I'm up. I don't want to. I want to leave plenty. Thank you.
So fantastic. Thanks so much. I have
Emily, you still out there?
Yeah, she is.
is
I told her I would call her out, see if she was really paying attention.
I have two questions. So one is you're seeing the network as given. What about just adding exits so that you can solve the problem physically in addition to analytically?
Adding exits?
Streets, right? So that for these critical
Mhm.
clusters, you
Yeah,
have more ways of getting out.
So one way, and that's actually what's codified in the law, is that these communities need to add these. And so one idea is that once you identify the clusters, then you could think about, are there streets like where there's a cul-de-sac and just some dirt and that under emergency conditions, we could create a new exit. So I think one part is, once you identify them, part of the mitigation could be, is there a way to add some exit capacity?
Right.
Because there are other mechanisms, like for example, it could be shoulder widening or reclamation of the shoulder. So there are some structural things one could do, like on these bottleneck segments, where you could ensure like there's a way to push traffic off if there's some stall or something else. So there are ways to enhance like the limited exits you see. But in addition, once you know the cluster, then you can search for, is there some potential to add a new exit, like a fire road or whatever under extreme conditions. So, but first you have to identify it, right? And so if you don't identify it, then you just are ignorant and don't know that there's a problem. And so there's no way to mitigate that.
Yeah. And then how generalizable is this to other cities, to the whole state, to other places that have, kind of a similar problem independently of wildfire?
It's very generalizable. That's all we're doing now. So for example, so this is Pacific Palisades, and I told you here was this fire road. So it's the network, and cleaning up the network is really the barrier.
Yeah.
So if you could ensure that you had quality data, which it's never true. I mean, we are working on ways like AI-ish with Google Street Views, where we might be able to more automatically at least flag where we have problems. Like even in the Santa Barbara area. So I've shown you some of these things, but I can tell you we should have zoomed into some neighborhoods, but some of these neighborhoods in particular, like it doesn't seem so bad, but they're actually exit roads that have a fence or some other barrier that they think is an exit road, but it's not. Right, so these are like worse than what we think. And this is really a high wildfire danger area. And so that's another element, right? Like, so, you know what I'm saying? So technically the road segment goes through, but there's a fence that's blocking that segment. So it's not functional. In theory, during an event, the fire marshal or somebody's going to be able to open the gate. During the events, guess what? Nobody does it because they're busy fighting fires and doing other things or responding to the emergency. So those things are well and good. And that's why in California now, if you have something like a fire road that's gated, that it has to have like an emergency brake box or something where they can unlock it to open it up. But it sort of depends. I think the other element of what you said, finding exits, is that being able to evaluate vulnerability of those bottleneck segments to whatever the hazard is. So for example, in Paradise, or Pacific Palisades rather, you know, the fire was here and soon this supposedly secondary exit route is inoperable. And so you can at least evaluate these segments and how susceptible they might be to whatever that hazard you think about. I mean, this area, total danger. I mean, this is Chaparral in and around. And the Chaparral burned, but it'll be back. Chaparral burns, it burns regularly. It has historically for thousands of years. And so we're preventing that from happening. But I think that's part of certainly what we're interested in and what we're doing in this initiative is saying, how can we coexist? Like what we're doing hasn't worked. Fire is an important regime. It needs to be there. We need to let fires burn and we need to let vegetation go through its natural processes. And so we have to build so that we harden our homes in various ways. We have to create defensible space. We have to, you know, accept that we are going to have fires and have what we constructed as a part of our environment is that able to coexist with these things that naturally should and could happen.
Yeah, so I'm curious about if there would be a way to account for the disparities in environmental burdens and social vulnerabilities in like across neighborhoods, in model or just in decision making.
Yeah, in this, so I didn't talk about it today, but part of our work is looking at the social vulnerability and disparities. And interestingly, in the Santa Barbara region, like as you may know, since you asked the question, there's census-based data that people have used to look at social vulnerability generically defined, not for a particular context. And so you could look at that. What we found in Santa Barbara that it actually doesn't really represent a good picture of social vulnerability. For example, we have a large unhoused population that live in certain areas, and none of those correlate to what like the traditional data tells us about social vulnerability. So in what we're doing, we're looking at these areas. Now that we can identify them, we're looking at, are there other sort of inequities or other sorts of concerns? Again, finding the critical clusters means now you can ask other questions. Like, okay, what are the characteristics of these people? And are they sort of more at risk, less likely to be able to recover from some issue? And therefore, and one of the other links that I picked the top one. There's another one that's looking at just social vulnerability. And so you can look at it in terms of wildfire risk and then social vulnerability and these sort of trade-offs. And it's in three-dimensional, you can search through it, but very important, I think in general, but certainly in our area, even though Santa Barbara is perceived to be this idyllic place where we don't have any issues, all is perfect. Although it is sunny and 75, that's pretty perfect. Weather-wise, pretty good. So yesterday arriving, I wondered why I was here, but to make me appreciate that. But, you know, it's not idyllic. There are these major inequities in that region for sure. Good question.
Yeah, I have a question about the impact of identifying these clusters on house prices. Because I remember, I don't know, 10, 15 years ago, there was a study in Santa Barbara that set the tsunami line. And there was a major pushback from the real estate community not to communicate that. So I wonder.
Just like
if you're
in a
gonna run-
floodplain, right?
Yeah,
Similarly.
If you're gonna run into something like that.
Probably. I think though, driving our work and then the people that we interact with. In addition to the mitigation aspect. In all of these things, as you know, it always can be used in this other way we didn't intend to jack up insurance prices or other sorts of things. I mean, that's already happening in Santa Barbara, that anybody in and around the wildland area can't be insured. So I mean, I don't know, we couldn't make it any worse because there's already a recognized issue. But where was I going with that? But I do think, I don't know, I had some train of thought. I was gonna say something interesting, but then I got off track.
I have another part to that question.
So I guess my point was that, you know, it could be, but I don't think so. Oh, what I was gonna say is that really the value here is that, as you know, Santa Barbara, the prices, well, I mean, it's true of all of Southern California that the prices are exorbitantly high. And part of that is a lack of supply. And so the addition of housing is a big deal. And so in some of the areas where there will be literally thousands of new people, these are areas in and around areas that are already 1,400 per exit lane. And so in terms of the emergency response people, they're sort of like, thank goodness. Like at least now we can better understand what these real impacts are. Like one of them is this, and that we have this development going right next to the area that's one of the worst off in the region. So hello, it's gonna be even worse, right? It's gonna be more like how it is in the Isla Vista campus area, but yet it's gonna be right next to the foothills, right? Where the wildfire is gonna happen. So I think that there is this better recognition of more complete picture of the impacts. So that probably outweighs any sort of negative view of it.
Well, as you mentioned during the talk, there are already 2 laws on the books in California regulating this, but how would this affect the new development that you're
Well,
talking about?
most of the law is really new development oriented. Not all of it, but most of it is new development, that if you're gonna do this, you have to ensure, and that's what they did in Pacific Palisades. That's
They have
why they
two.
have the fire road, because they had to have more than one exit, because that's what's mandated by this law. However, is it really? Like, I mean, if it's in this area that's gonna burn, that's gonna be the first part of the vegetation to burn and close off egress, then what good was it? So,
Yeah, I have a question about like the kind of temporal dimension here, because
what dimensions
the
are?
temporal, like the
Uh-huh.
time dimension, because people have like different tolerance to risk in terms of like when they evacuate. So I know that some people like wait till the very last possible minute when they're like actually seeing the flames. So I know the data is probably really hard to get, but do you have any source of data that shows you from these like past events, the kind of time frame along which the evacuation is happening, and then whether that can confirm?
Yeah, so we know quite a bit about that, and that a lot of people, a significant amount of people don't leave at all. But you know, Santa Barbara does have somewhat of a problem because we've evacuated more frequently, that people sort of are not so worried about it, and they probably should be more worried when they hear these things. And I think secondly, emergency personnel are quite conservative, and like the fire's still in Ojai and they're already evacuating areas. So like really in advance, before, and so that when you look at evacuation, clearing times and whatever, it sort of doesn't matter because they always do it in advance. But I think that the issue about the timing and that people do different things and behave differently, that is a big deal. But also it does change like how many people are in an area. So in our initial analysis, it's really the census-based residential information. What we tend to know is that, so that's really a diurnal part of the picture, right? Nighttime where people mostly are on weekends and non-working hours. But it does turn out that many of these neighborhoods, because of various kinds of workers doing whatever kinds of activities, that it's almost about the same. That, you know, so if I thought there were 1,400 people, yeah, even during the day, during working hours, there's probably about that when you count up, you know, when we've done surveys and studies about who's really there during different parts of the day, in addition to recreational activities and hiking trails and sort of other sorts of things. So I think that the timing, the time of day matters in terms of who, but we do know that sort of cancels out more or less that there's other things happening. And so you're probably pretty close to what it is. Secondly, in terms of when people go, people tend to wait. That's for sure. Some people, 20% or more, don't go at all. And this is a part of, like, so when I said that we have the data, we do some processing, we do the modeling to identify these areas, and then we do actually simulate the behavior. And in that simulation, that's when we're looking at, we have this event, we're going to move these people to like this safe location, and then we'll look at these individual characteristics and the behavior of people. And in our simulation, this is like the cars on the network, like backing out of my driveway, I create this bottleneck and now I'm going, and then, oh, here's a car returning because they want to pick up their dog. And so like you can actually visualize this and see that this is really what people are doing during these events, and that some people aren't taking the direct route. Some people are going some of these crazy ways and doing various things. So that's an important part of that. And I think that aspect of it is what captures that. And we're not really modeling. It's part of a modeling question. I think whether it's a, you know, a statistical one where I'm trying to describe things, or whether it's a predictive or a prescriptive one, like what I'm doing. We're always trying to simplify, like what are the basic things we care about. And so like some of these elements, well, that's not really, we want to identify this area, the neighborhood, and then based upon its structure, then we'll look more deeply into like what are the things that it could potentially face, and then also what are these behavioral characteristics. But it is part of this sort of bigger picture. Not what I talked about here.
Online in the chat.
What's a question from Emily?
I have one.
Oh, I didn't know you were on volume there. All right. Hit me.
Sorry, I had to step out for a minute, so I don't know if somebody already asked this, but as an urban planner, what strikes me is that this is more evidence that sprawl is such a disaster with its single points of ingress and egress. And do you ever look at the scenario of adding in a street network that's more gridded as a way of mitigating that bottleneck situation?
So your first question, what was the first question again? Oh,
Gridded.
Sprawl is
and
bad.
gridded.
sprawl is bad. It turns out that building developments in the middle of wildland shrubs that like to burn is not a good idea. So you're right about that, and we know that. And there's a lot of evidence, and certainly what we saw in LA is supports that observation. But I mean, it's going to continue to happen, as you know. Secondly, Julia did ask a related question, and the response was, once we identify these areas, then we can look at ways in which we might be able to add potential additional ingress and egress. So,
Okay. Have you seen research looking at that particular aspect? Or is this, I mean, in my world, in the city planning world, there's tons of writing about the importance of street grids and retrofitting sprawl and suburbia by putting in gridded street networks. And I wondered if any of that has translated into or trickled into to your world.
yeah, I haven't seen it. And so basically where we're at is that we've identified this difficult to evacuate area. And there is, concern under whatever conditions. And sort of the next step is, can we identify ways in which we could enhance the exit potential as one mitigation strategies, but not necessarily anything particular about that network structure. Just, is there any way we could add it? So I think what you're talking about, no, that hasn't made its way into this area at all.
Okay. Well, we
So I
should talk.
look forward to talking to you more about it.
Yeah. Sounds good. Thanks.
Sure.
Alan, I have a question. The way I see this is in essence a network vulnerability assessment.
Yes,
So this is not restricted to wildfires at all.
not at all.
That's
So that's
what
why I highlighted these other cases
Yeah,
that, and in
yeah.
Santa Barbara, like the campus area, there's no threat of wildfire. I mean, there's always a threat of some fire, but there's no, significant wildfire danger to campus or Isla Vista, but there are many other things. And so that's why, in terms of our work, it is, vulnerability across the spectrum of potential hazards that we could experience.
I was thinking specifically about the flooding dangers in Appalachia,
Uh-huh.
where it wouldn't be a neighborhood, but it would be whole communities
Right.
that are in bottlenecks or in cul-de-sacs.
Right. No, super important. And that's definitely how I conceived of this. And the only thing holding one back is good data
Yeah.
that supports that. But, analytically, right, it's one line. What's my network data and then some other specification? It's pretty much ready to go. And computationally, there's nothing prohibitive about, like, I haven't even hit the upper bound of what's possible in terms of the solution. I mean, these are just seconds. That's, nothing. And it's seconds on just this crappy old 9-year-old laptop. Go ahead.
Yeah, if we're talking about applications to other regions or other disasters as well, I wonder what our ownership is very percent, right? All of the
California is car centric, yes.
But if we're talking about applications to other regions, um, or other populations, right, and also people might sensitive. So I wonder if there's, first of all, in your experience, what are ways for other populations to evacuate? What would be a means to if we don't have access to a car? And how would that be? How would we be able to?
So in terms of this work, one of the reasons for identifying these areas would be looking at what is their sort of mobility issues and concerns, and then how are we gonna, part of the mitigation is how are we gonna deal with that? Like, is there a retirement community? How many people are immobile in some way for whatever capacity? How what's the strategy for dealing with that? So I think that part of this, as I told you, was a part of a bigger picture, and that the mitigation component at the end is, now that I've identified it, what are these issues in terms of how we're going to get people out. The public transport is a more difficult one, I think, in that whenever there's some hazardous situation, almost everything schedule-wise is out the window. And so it would be, I wouldn't even venture a guess, because at least in the areas that we're looking at, it is very car dependent environments, and so we haven't had to look beyond that, other than identifying, you know, sort of the transport disadvantage and what that means for particular areas and how you would overcome them. But I mean, I think it is a very much a part of the process, but I do think that these more things like in Chicago, where there's much more public transit and reliance on different modes, is difficult to conceive of in this way, other than the assumption here is that the spatial footprint matters in some way, both in terms of difficulty in getting people out, but also in terms of the hazard that they would be, the hazard or hazards they would be faced with. And so based upon that, it's really context dependent. Just as it is like the hazard and where it is and where, how it will get to you, because that will indicate or serve as a basis for where you're going to evacuate people. In general, in Santa Barbara, you would think that the coast is pretty safe, but I mean, Pacific Palisades, Malibu Fire have told us, maybe it's not. Lahaina, you know, things are changing, and these old ideas of that, well, we could just head to the coast and we'll be safe. Well, maybe not, because these are the extreme events that we're having to deal with now. But there are, you know, places that are pretty safe, like GeoDa. There's some areas because it's protected basically by tree groves and other sort of agricultural land that's really not gonna, it's gonna prevent the fire from coming through. So there are some, but even that, you can't say, well, you're always gonna go there, because I mean, there could be something from the west, depending on the wind conditions, because all of these extreme events in Southern California are really based upon the extreme wind event conditions. Because if there's no wind, I mean, it's a fire, it's not going to be a big deal. But when you add 90-mile-an-hour winds and dry conditions and continued drought, all is out the window. No matter how many people you have, you know, the infrastructure just can't handle it. And so you're going to have these events that we're seeing, these extreme events.
And Santa Barbara as a whole itself is kind of constrained by 2 or 3 exits,
Yes,
one of which is in the fire. Actually,
exactly.
2 of them.
That's right. Yeah, so like I have a paper and I'm happy to share it with anybody, but you know, the main entry and exit is 101. It's this freeway. I mean, that's really it. And your other exit is probably where the fire is going to be. And so you're not going to go that way. And I didn't talk about it, but in 2017, we had the Thomas fire. So that came more from the LA area, but it came all the way to Santa Barbara. And it came, you know, to the coast, like some of these other ones that we saw, not the Santa Barbara southern, more in Ventura. I guess that's technically maybe the edge of Santa Barbara County. What was my point?
I think 101 was shut off.
And so 101 was definitely impassable during the fire, but then what we had soon thereafter was a rain event in the Montecito area where it had burned that created a debris flow that closed 101 for 2 weeks. And it washed out the secondary bridge, so there was no way to get there other than going way around. So that was a big deal. You're right. But I think mostly it's that you have the Santa Ynez Mountains, which go up to about 3,300 feet, 3,500 feet, whatever it is. And it's mostly chaparral, you know, a vegetation, you know, it's kind of a bush, and its natural regenerative process is fire. It grows, it dries out, it burns. It has for thousands of years done that. And we live right next to it. It's a problem.
Great. Thank you so much.